In related rates story problems, the idea is to find a rate of change with respect to time of one quantity by using the rate of change with respect to time of a related quantity. The procedure to help you solve related rates problems. Number 1, draw a figure if necessary and choose variables for all unknowns. Sometimes it's helpful to visualize. Number 2, write what is given and what is to be found using d over dt symbols, using our variables and d over dt symbols. Number 3, write an equation relating the variables. If a quantity is changing, it must be represented with a variable letter. If a quantity is constant, it must be represented with a number value. Look for secondary relationships between quantities to reduce the number of variables. The main equation, I like to call it our objective equation. What are we deriving with respect to time? Then we implicitly differentiate both sides with respect to t, time. And your final step would be to substitute any sort of number values and solve for what they're asking for. Here are most of the geometry formulas that you will need for related rates problems. These you need to have memorized because you will need to be able to access any of these formulas in your mind during the AP test. Example 1, in these problems, the first 3 steps of the procedure are done. We need to complete only the last 2 steps. Here's what they've given us, and they want us to find dA dt, so the derivative of A with respect to time. So they want me to derive A with respect to time, and so I look for the equation with A in it, and that's what I'm going to derive implicitly. I'm deriving both sides of the equation with respect to t, time, which means my variables are not going to match. Because we're deriving with respect to time, and time is not one of the variables in the original equation, then every single variable, when derived, will also require chain rule, the derivative of the inside, to be multiplied on as well. The derivative of A with respect to time is dA dt. The derivative of s squared with respect to time is pop down, power down, times the derivative of the inner function. So what's the derivative of s with respect to t? Oh, that's simply ds over dt. Now it's time to substitute back in. Notice that we have an s, and they gave us a value for s. So they want to find out when s is 4, how is the rate of the area changing? They also gave us ds dt. Time to substitute and simplify. What does this statement mean? This means that the rate of change of the area is 24 units squared per time. That is how area is changing. That's why we use units squared, because area is always units squared. They've given me a relationship between x and y, a value for y, and a rate for dx dt. And they want me to find dy dt. So I'm going to take my original equation, xy equals 12, and I'm going to derive both sides of the equation with respect to time. The left side is a product, so I'm going to use the product rule. The first function times the derivative of the second function with respect to t, time, plus the second function times the derivative of the first function with respect to t, time, is equal to the derivative of a constant, which is 0. Go ahead and derive these. The derivative of a y with respect to t is dy dt. X times dy dt plus y times dx dt. Again, those variables don't match, so I need to include the derivative of x with respect to t, which is dx dt, equals 0. Now we're trying to solve for dy dt, so I want to get dy dt by itself. Use some algebra. And dy dt is equal to negative y over x times dx dt. Now it's time to plug in the values you know. Y equals 4, dx dt equals negative 6, and x, wait, but what is x? Well, we know what y is. Y is 4, so we need to find out what is x when y is 4. Our relationship between x and y is this equation, x times y equals 12. So if y is equal to 4, x is equal to 3. And that will be plugged in for our x value. This is the rate for which y is increasing because it's positive. So the rate of change of y with respect to time is 8 units per time. This is not an area, this is a length. A windlass is used to tow a boat to a dock. The rope is attached to the boat at a point 15 feet below the level of the windlass. At what rate is the boat approaching the dock when there is 25 feet of rope out? Write a sentence explaining the meaning of your answer. There's already a diagram, so I want to write down what we know and what we need to know in the terms of the variables. So the rope is attached to the boat at a point 15 feet below. This 15 feet is not changing. The windlass is in a permanent position, so this will stay as a constant of 15. If the windlass pulls in rope at a rate of 30 feet per minute, okay, so we've been given a rate, 30 feet per minute. This is the rate at which the windlass pulls in the rope. So I go to the side or the part of the diagram that represents the rope, and I see that that would be z, or the hypotenuse of our right triangle. So if it's the rate of change of the rope, and the length of the rope is represented by the variable z, then the rate of change of the rope would be dz dt, the rate of change of the rope length with respect to time. There's one other piece of information. Is this an increasing rate or a decreasing rate? Is the rope length getting longer or is it getting shorter? Well, if the windlass is pulling the rope in, then it is getting shorter. The length of the rope is decreasing. So you have to make this rate negative. The question here is, at what rate is the boat approaching the dock when there is 25 feet of rope out? So the rope, they're saying, is at 25 feet. They say when the rope is 25, we want to know the rate at which the boat is approaching. Okay, so the length from the boat to the dock is x. So the rate at which x is changing with respect to time is dx dt. And that's what we need to find. Where's my equation? Do you have a way to relate the lengths or the side lengths of a right triangle? I believe you do. It's called Pythagorean theorem. A squared plus b squared equals c squared. So x squared plus 15 squared equals z squared. The sum of the squares of the legs is equal to the square of the hypotenuse. And I could simplify it by squaring 15. So now I have an equation that relates the variables that I'm using, x and z. I'm not going to plug in z equals 25 because this is what they want me to find. Find dx dt when z is equal to 25. But z is still changing, so it must be represented by a variable. It's time to derive both sides of the equation with respect to time.
The derivative of x squared is 2x times the derivative of the inside dx dt. Plus, the derivative of a constant is 0 equals the derivative of z squared with respect to time, 2z, and then dz dt.
We already decided we were looking for dx dt, so solve for dx dt. All right, we've solved for dx dt, and we have dz dt here and z here, but I don't have a value for x, and so I'm kind of stuck. They said, at what rate is the boat approaching the dock when there is 25 feet of rope out? So the instant that I'm looking for in this moment in time is when z is 25. That's why I will plug in 25 for z. But if I know what z is at this moment in time, I can find out what x is at this moment in time because I have a relationship between x and z, the Pythagorean theorem. So when z is 25, what is x? And in context of the problem, the distance would be positive. So when z is 25, x is 20, and that's what we plug in for x. dx dt, 25 feet over 20 feet times the rate of change of the rope. This simplifies to be 75, negative 75 over 2, or negative 37.5. This is dx dt, the rate of change of the distance to the dock. So distance per time will be our units for this rate, feet per minute. Write a sentence explaining the meaning of the answer. One possible sentence would be the distance of the boat from the windlass is decreasing at a rate of 75 over 2 feet per minute. And since I used the word decreasing, I did not need to put a negative, but if you don't use the word decreasing, you got to make sure you say that rate is negative. Gravel is falling on a conical pile at the rate of 10 feet cubed per minute. At all times, the radius of the cone is twice the height of the cone. Find the rate of change of the height of the pile when the radius of the pile is 6 feet. Write a sentence explaining the meaning of your answer. So first I see conical pile. It looks like we're dealing with a cone, and it's being filled, so it looks like volume of a cone. Now they said the gravel is falling at a rate of 10 feet cubed per minute, which means the volume of the cone is growing at a rate of 10 feet cubed per minute. How else could you tell that this is the rate of change for the volume rather than the height? The units. This is 10 feet cubed per minute, giving you the rate of change of the volume because the units are cubed. Find the rate of change of the height of the pile when the radius of the pile is 6 feet. R is 6. When you derive this with respect to time, you will end up with a dv dt, a dr dt, and a dh dt. But I've only been given dv dt, and I need to find dh dt, and dr dt is nowhere to be found. I have too many variables in my starting off equation. I need to narrow it down. The good news is they gave me a super helpful piece of information that will help me simplify the variables in my objective equation. So yes, this is the volume of a cone, but this isn't just the volume of any cone because it has a special relationship between the radius and the height. I like to call that unchanging relationship the constraint. This will help us to reduce the number of variables in the objective equation. The radius of the cone is twice the height of the cone. So the radius r is equals twice the height, 2 times h. I have a relationship between r and h, so I'm either going to turn this equation into a function of just r or a function of just h. But which one? Since I want to find dh dt, I don't want to get rid of the h's. So instead, I want to plug in the equivalent value for r in terms of h. That's what I'm going to do. My objective equation is getting simplified or rewritten so that I have fewer variables. R is 2h. Simplify this. Now we have an equation with a v and an h. They gave us dv dt. They asked us for dh dt. So I think I have enough information to truly find dh dt. It is time to derive. So the coefficient for this term would be 4 pi times h squared, bring down the power, and then also times the derivative of h with respect to time. They asked us to solve for dh dt, so I'm going to do that now by dividing both sides by 4 pi h squared. Now that we've completed deriving implicitly, we need to plug in all the values we know. For example, dv dt is equal to 10, and r is equal to 6. My derivative doesn't have an r in it, it has an h. So how am I supposed to plug in a value for r when it's really a value for h? Well, do you know a relationship between h and r? Yes, you do. R is 2 times h at all times. So if R is 6, what is h at the exact time that R is 6? H is 3. Now we have all the pieces we need to plug in. So dH/dt is 5 over 18 pi, and the units for that, the rate of change of the height, and that's just a length, so that would be feet per time unit, which is minute. 5 over 18 pi feet per minute. To write a sentence explaining the meaning of this answer, the height of the pile is increasing at a rate of 5 over 18 pi feet per minute.